So last time I discussed this HRT covariant entropy formula where you define the entropy by minimizing or by extremizing the area of a surface gamma, and then if there's multiple x's, if there's multiple extremal surfaces, then you pick the minimum one. So this is the HRT formula, and I'm going to declare MR to be the solution to this. Then there's another formula which is equivalent in certain situations that are sort of physical space-times. And in the Maximun formula, we instead define our surface by, on each ADS Cauchy, we minimize area, and then we vary sigma to maximize the minimum. Okay, so this I'm going to call capital MR, and the idea is that on physical space-times, we'll be able to prove that that these definitions are equivalent, so that the Maximun surface is also HRT, or on physical might be a little presumptuous. We'll say on good space-times. I'll moralize a little bit. And so, but the proof that these are in fact equivalent is non-trivial. It's not supposed to be immediately obvious. Intuitively, you can say if you're minimizing in some directions and maximizing in other directions, it's likely to end up being extremal. But there's some details there that I'm going to show you in this lecture. Okay. Are there any questions about this or these definitions or the content of the previous lecture before I go on? Last time, I wrote down some assumptions about the space-time that I'll be using. I won't write down the full list again today, but hopefully you'll see them as we proceed. And one of the reasons I'm going through this is that there's a lot of ingredients here that are also useful for other things. So even if you don't care about the conclusions, you probably, which I hope you do, you probably care about some of these tools if you ever want to do proofs of things in general relativity. They use a lot of the same constructions over and over again. Okay. So one of the assumptions here that we are assuming is the null energy condition. Or the null curvature condition, which you get from the Einstein equations. And this has a very important implication that's crucial to the Penrose singularity theorems, to various theorems about causal structure in general relativity, to a variety of contexts. And that implication is that null surfaces focus. You've heard that gravity is always attractive when you have positive energy, but then, you learn more about GR and you realize there's these solutions like brains that, membranes that repel things, and that, or the cosmological constant that causes the universe to accelerate, which looks like anti-gravity, even though the cosmological constant is positive sign. That's because you're thinking about time-like acceleration. But if you think about null surfaces. So if I have what's called a congruence of null surfaces, which is a bunch of null geodesic, a congruence of null geodesics, which is a bunch of null geodesics that are next to each other. If I start, so one way to get such a thing is if I start with a surface and I just shoot out in the normal direction light rays from that codimension 2 surface, then I'll get a codimension 1 null surface. You might call it N. It's ruled by null geodesics. There's a coordinate V that you could add to say how far you're going. And one generally wants to use what's called an affine null coordinate, which means that you define it by sort of parallel translating your vector along uniformly along this thing. So an affine null coordinate is like the analog of a proper time for a time-like geodesic, but this is for a null geodesic, and it's defined only up to an affine reparameterization. And if you know about Christoffel symbols, and from ever having studied general relativity, a way to put the condition is that the VVV Christoffel symbol is 0, meaning that if I take the V vector and I translate in the V direction, I don't pick up an extra V term. So once you have this null surface, we can talk about it has a null extrinsic curvature, which is given by I'll write this down. So Kij is given by the null extrinsic curvature is given by 1/2 the derivative of the metric restricted. So there's a metric Hij that's restricted to the transverse directions. And if I take the derivative of that with respect to V, I get the null extrinsic curvature. Actually, I think this V here is more naturally downstairs. So maybe I'll put it there to avoid confusion, because it's like a derivative. And so this thing, you can take the trace of it, and you can take the traceless piece of it. So the trace of it is the trace Kij, and then we can take the traceless piece. I won't write out the formula. You probably know how to do that. So this is called the expansion, theta, which is also the rate of change of the area per affine coordinate V per unit area, where A is a sort of infinitesimal area element associated with a tiny region. So as we go here, we can ask how much the area changes per unit area. That's called the expansion. And the shear, which you will only get if you have at least 4 space-time dimensions, governs the rate at which the geometry of an initial sphere will deform into an ellipsoid. Does this make sense? So one of the key equations that I use all the time is called the Wretched equation. Yes? At the moment, well, you can define it for various cases. At the moment, we're discussing a codimension 2 surface embedded, well, we're discussing, so the slices of this null surface is codimension 1, but I'm considering a codimension 2 slice And then we're asking how is that embedded in the full space-time. So there's two components of the extrinsic curvature, because in the normal direction, you can either point in the v or the u direction. And the v, if it points in the v direction, it governs the change of the geometry in the v direction. There's also you could also consider the change in the u direction, that's going off of the null surface. Does that make sense? Okay. So the Wretched equation is a statement about a sort of a second derivative of the area, although you have to be careful because there's a 1 over a in here. So this thing is really like d by dv, 1 over a d by dv. This is given by the following expression. There's some quadratic terms. This is the space-time dimension minus 2. There's also a shear squared term. By this, let's just write it out like this. And finally, there's the VV component of the Ricci tensor, which is related by the Einstein equation to 8 pi g times TAV VAVV. So what you can see is if you satisfy the null energy condition, that this is greater than or equal to 0, then the whole right-hand side of this equation here, so the whole right-hand side of this equation is less than or equal to 0. This tells you that if the energy flux represent in the null direction is positive, then light rays always focus. They never defocus. Now, once they start focusing, it could eventually reach some point where they start crossing each other, and you get a caustic. And then after they cross, they could start expanding again. But in most of these constructions, it's convenient to say that once they cross, you just remove them from the null surface. And then you just have a null surface that has some caustic here. And you can consistently just stop following the null surfaces. Stop following the null geodesics. And this will still be a null surface that separates space into an inside and an outside. Okay, so and if we're using the null generic condition, then this is actually less than 0 because this will be greater than 0. Yes? Well, I mean, this sort of thing happens even in flat space-time. You know, one example physically is if I have a star, and I just have light rays going through the star, there's a Shapiro delay where it gets slowed down, the light rays that are near the star. And then if I just, when I'm far from the star, if you just keep drawing out light rays normal to this, you'll find that eventually these things form a sharp corner. So at the point, so these things form a sharp corner. If I followed all of the light rays, then I'd find, if I kept following the light rays that leave the null surface, I'd find that the null surface has another component that looks like a loop-de-loop here. Okay. Yes?
Is that the only way that you use the generic condition, or does it show up elsewhere?
It only ever comes via the Wretched equation, but there's multiple uses of the Wretched equation, I think.
Yeah.
I wouldn't swear to it. if this were a courtroom. Yeah.
Because you want a strict inequality.
It's generally speaking because I want there to be a positive amount of focusing as I go from one place to another. It's just a sort of a technical convenience. So this ends up implying two very important results. One of them is that if I start with an extremal surface, so an extremal surface has the variation of the area is 0 to first order as I go in any direction. So to specify that the surface is extremal, it suffices to pick a basis and say that the area is 0 in that direction. So if I pick my the null directions, then to have an extremal surface is equivalent to saying that the v component of the expansion, which is what I defined above, is 0, and the u component of the expansion, which would be the same thing as that, but replacing u with v and going in the other null direction, that's also 0. So, but that tells you that if you start with theta equals 0, and I integrate this equation, theta is always going to become and stay negative. So that tells me that if I shoot out a null surface in any of the 4 possible null normal directions, then along any of these null surfaces, the area is decreasing. As we move away from x. Okay? So it decreases to the future and also to the past. So that's the first important implication. And the second important implication is called the second law, because this is the classical form discovered by Hawking of the second law of black hole thermodynamics. And he actually proved this as a GR theorem before, in the black hole case, before he even discovered Hawking radiation. But both were in the 70s. So in our context, with an asymptotically ADS space-time, so the statement is that the area of any causal horizon, any future causal horizon, increases with time. So by a future causal horizon, I mean we're going to take some locus of points on the boundary of the manifold. Okay, so some locus of points, maybe just 1 point. That was, and then we're going to take the past of that point. So that's everything in this region. And then we're going to take the boundary of that past. And so this is infinity. This is the boundary of the past. And this is a causal horizon. So it's the boundary of what can be seen from some set of future infinite world lines that hits the boundary. So the statement you can now make is that this area increases with time. So the area is increasing going in this direction. I'm not going to get into the details of the proof of this here, but it follows from the Wretched equation. And the essential idea is that you're basically integrating the Wretched equation backwards in time. So the area has to be increasing or stationary as you reach infinity. And then using that, I just integrate this equation backwards in time to say that if theta is positive here, it stays positive here. Or another way of putting it, if it's ever negative, it would focus into one of these caustics. but that's inconsistent with it being a future horizon because of this null surface leaving thing. Okay. So those are two useful results. There's a third useful result. Which I'm going to call the kissing lemma because it's about two null surfaces kissing each other. So we're going to let n and m be two null surfaces which touch along a particular, so let G is going to be a null geodesic. This is going to be space at one time. So we pick a point along G, and at space at one time, I'm going to have two null surfaces that whose cross sections intersect in the way shown. So what I want this to be is that M is nowhere inside of N, but they touch along G. So these two null surfaces share a null geodesic. Just one null geodesic, which I've sort of shown going off to the future here. And one of them is always either to the past or coinciding with the other one. And they do coincide at this point. And we're interested in how things behave at this point. Any questions about the premise of this? I could try drawing a three-dimensional picture, but that might be embarrassing. So, okay. So the statement is, given this, we can deduce that the expansion of M is less than or equal to the expansion of N at this point. And this is, although I've given some proofs of this in my papers, it's actually a very intuitive thing. Because if I just imagine that the null surfaces, the light rays shoot out normal to these null surfaces, then you can see with your own eyes that this null surface would have to bend away. The null surfaces have to bend away from each other. And as a result, the normal light rays are focusing more for this surface than that surface. Okay? No, sorry, that's a bullet point. That's confusing. How about that? Okay, and the second statement is that if these thetas equal each other, then, so that situation is like, well, you could say it sort of looks like generically the second derivatives of these surfaces, the positions of these surfaces are going to differ, but we could consider a sort of case where they coincide sort of more closely. And so the statement is that if it's equal, then either there exist nearby points where theta m is less than theta n, or they coincide in an entire neighborhood. Okay? So this is also intuitive. It just says, if they bend away the fourth order, I'll be able to find some points nearby where I define the relative V affine parameter. Since these surfaces are close to each other, I can parallel transport vectors between them without worrying too much about the fact that they're at different points to define this. And then at some point, either one of them deviates away from the other one, in which case this is true, or they just coincide in the complete neighborhood. So sometimes that's useful. Now, let me just take a detour here because I don't think I'll have time for it at the end, and observe that, a lot of this, the whole program of it from Qubit is to find that certain things about space-time that look like purely geometrical facts are really telling us something about information theory. So you could ask about the quantum corrections to these things. And so the part of the focus of my research has been to show that all of these things continue to be true when you add quantum corrections. So if I define the generalized entropy as the area over 4g h bar plus an entanglement contribution on one or the other side of this null surface, which I can do so long as my as long as my codimension 2 surface separates a Cauchy slice into 2 pieces, then I can ask about the entropy I can talk about the entropy on the inside and the entropy on the outside. So if it's a pure state, Sn equals S out. So if it's a mixed state, they're different, and I can pick whichever side I want to call the inside and the outside. So the point is, all 3 of these things also seem to be true semi-classically when you add this bulk entanglement term. So when it's the second law, we call that the generalized second law that says that the area of the event horizon plus the entropy of any matter outside will be increasing with time. So quantum mechanically, a black hole could Hawking radiate and the area can actually decrease, but you make up for it with Hawking radiation, the entropy of the Hawking radiation outside. Or I can dump something in and the entropy, the area might grow, but it grows by enough. The entropy outside might go down, but the area always grows by enough to make up for it. The fact that that there's focusing is, actually I could go all the way up to here. The fact that this is less than 0, we can instead replace our focusing statement with a statement that the second derivative with respect to the v of y's, if y is the transverse direction here, of the generalized entropy, where I mean these deltas to include this 1 over a piece, the per unit area. This thing is saying this is less than or equal to 0 is the quantum focusing conjecture. So this sort of generalizes this Wretched inequality, and there's been a number of talks about this. Nobody has yet, for the most part, it's unclear whether we can actually promote this to what extent can we promote this to an equality that involves some quadratic terms would be an interesting question. In certain field theories, it looks like this, the quantum null energy condition that is the form of this when I restrict to a stationary null surface is saturated. There's been a bunch of discussion of that, though, so I won't say it anymore. And this thing also is true if I replace the area with the generalized entropy. Then the kissing thing is true, at least order by order in a GH bar expansion. So these have all been proven in various semi-classical regimes where you do a GH bar expansion. Oh, and this thing the statement about extremal surfaces, you can also replace that with the criteria that the deviation of the surface. Oh, I'm crazy. Let's see. VU. I'll just write n for the normal directions. The normal deviation. All right. This is bad notation. I'll write it like this. The first order variation of the location of the extremal surface of the generalized entropy is 0. Okay, this is a little bit. The statement is that this would define a quantum extremal surface which is the analog of a surface for which the area is extremal. That is used for the holograph to define the quantum corrections to this HRT formula. So all of this was a big digression to say all of this stuff can be has begun to be understood at the quantum level as well. But I'm going to go back to classical physics now. Yes?
The kissing lemma follow from the Wretched equation or independent?
Are we talking about the yeah, so this one does not require the Wretched equation. Yeah. So this is a purely geometrical. Well, actually, the Wretched equation is also a purely geometrical fact. Before I substitute in the Einstein equation, but this is a different purely geometrical fact at the level of area. If I would like to prove this also for the entanglement piece, then I break it up. I consider the area piece and the entanglement piece separately. The area piece is the same, and to get the entanglement piece, I use a form of strong subadditivity. Essentially, the statement is it's sort of strong subadditivity between if I vary this region, then it's sort of strong subadditivity between what I have and my call this A. So a strong subadditivity between the new information you get from varying in the null direction, the information that's inside one surface, and the new additional information outside the surface. Yes.
So you mentioned for the third theorem, we don't really need Wretched equation. So it's not clear to me how the entanglement will go inside this equation. It seems it's just.
These are just two separate things. So you can both this. If I promote the area to the generalized entropy and say what sort of half geometry, half information theory facts continue to hold, then there's a proof that this continues to hold, at least order by order in GH bar, and there's a proof to at least the leading quantum correction for certain field theories that the quantum focusing conjecture inequality is true. So it's just, on one hand, it's two separate things, but it's striking that the same quantum generalization works for both of them. Okay. I'm going to proceed now with classical physics. Okay, so one fact that you can prove using these sorts of things that doesn't actually require the Maximun method is that extremal surfaces are deeper in the bulk than causal surface. The causal surface so to define this, there's sort of two constructions we could have here. There's this extremal surface that we've already defined, But another thing we could do is we could take the past of this domain of dependence, and we could take the future of the domain of dependence. We could take the intersection of those. This is I minus of dA intersection with I plus of dA. And that gives you what's called the causal wedge. And it's sort of space-like boundary of all this is this codimension 2 surface where they intersect. So the statement is, so in certain special cases, like a ball region in ADS in the vacuum state, these codimension 2 surfaces, I guess, yeah, these codimension 2 surfaces coincide. But non-generically, they don't coincide, and the extremal surface is always deeper. So you can prove this by you pick your region on the boundary. So I'm going to call this one WR, and this one I've been calling M of R. So I let this be W of R. And so let's draw this as one Cauchy slice. So on a Cauchy slice, I can't know for sure that this extremal surface is going to lie on the Cauchy slice. But if I extend the extremal surface in the null direction, that's going to lie on the Cauchy slice. So let's take this nx, and I'm assuming for contradiction that proof by contradiction. I'm assuming for contradiction that this null surface is closer to the boundary than the causal surface. But what I can do is I can continuously shrink the value of the region. We saw before that the location of the extremal surface can jump with a phase transition, but that doesn't hold. There aren't jumps when I'm talking about the causal surface. So if I shrink down to a smaller region here, if I continuously shrink, then at some point they're going to coincide and touch without crossing. At that point, I have, so I'll call this W prime. So theta of W prime is less than theta of nx by this kissing lemma. But theta of W prime is greater than 0 by the second law, because it's a causal horizon. It's a piece of a causal horizon. So its entropy is increasing. And theta of nx is less than 0 by focusing. That's this. So I'm using 1 to do nx, and I'm using 2 to do W prime. And the three of these together are a contradiction. This is an example of a case where it's convenient to use the generic condition. That way, I don't have to worry about these all being equal and making it not a contradiction. But it has to. But as a result, by continuity, this still has to be true in the case where they are not, where you don't assume the generic condition, like vacuum ADS. But in that case, they might end up coinciding with each other. Okay. Any questions about that? So that didn't require the Maximun method. But I'm going to tell you now what extra we get out of the Maximun stuff. So the Maximun surface has the following properties. So number one is, in a variety of situations, we can prove existence. So none of you ever objected when I introduced the HRT proposal. None of you asked me, what if there are no extremal surfaces? Well, it's just a sort of mathematical nicety. Usually physicists just assume the stuff we're interested in exists, and we leave it to the mathematicians to prove it actually exists. But in the case of the Maximun thing, you can usually prove that it exists. So the key is to use the extreme value theorem. So this theorem says that a minimal or maximal value exists. We don't worry about ties here. If exists of a function on some space X, if we can find a topology T such that A, X is compact. X is not the extremal surface here, it's the space. And B, F is lower, or in the case where we want the maximum, upper, semi-continuous. Okay? So what we do here is for the min step, we use a topology that's roughly speaking, the details are in the paper, but roughly speaking, it's defined by the distance between two candidate surfaces, S1 and S2. So it's defined as a sort of minimum distance. Sorry, maximum distance. So that's a sort of measure on how far away the spaces are. Now that's a metric, not a topology, but as you perhaps know, whenever you specify a notion of distance on a space, you can use that to get a topology. So using this topology, you can show by conformally compactifying the ADS space, you can show that the minimization step is always well defined. For the max step, we use a time function. We think of our ADS geometry. We define a time function on this. We think of our Cauchy slice as being a function of time. And then we compare two Cauchy slices by considering the max time between them. And then there's something called the Ascoli-Gsella theorem that guarantees that under certain conditions, this is a compact space. Now, I guess I won't go into the details of this, but I will say this assumes something else about the space-time beyond the assumptions I get. In the case where there's no horizons, you can always complete this maximization step, but something that can go wrong is when the sort of Wheeler-DeWitt patch of places that this causal so in cases where this Cauchy slice could potentially go up and hit a singularity, you could worry that the maximization will push you into the singularity. It turns out that as long as the singularity takes what's called the Kasner form, this is okay. On the other hand, if instead of a singularity, I have something like a de Sitter future, then that's potentially bad. Because you maximize, the area goes to infinity as we go to de Sitter. So there's some caveats here, but on a variety of spacetimes, you can prove that these things actually exist. Since I'm not giving this talk to mathematicians this time, I won't go into more details unless somebody asks. The second thing that we can show is a sort of, this is a place in which I wasn't as rigorous as I could have been, and there may still be a mathematical hole here. So there's, it's important at certain points that the Maximun surface be what I called stable. So at in this construction, we start with our Maximun surface, and I'm often interested in varying the Cauchy slice and using the fact that this still exists after I vary. So if I vary my Cauchy slice from sigma to sigma prime, I'd like to say that I can still find since this is a maximum, that if I deform this Cauchy slice, I can find a surface here, a minimal surface here, that has less area than less than or equal to the area of the surface here. So the area of min sigma prime is less than or equal to the area of m sigma. This seems like a reasonable assumption, but in certain weird cases where there's more than one Maximun surface, it seems like some of them can be unstable, and this minimization is not guaranteed. I could prove that there always exists if there's only one Maximun surface, it's always stable, and if you assume that the Cauchy slices are space-like, instead of having null components, then it's always there always exists a stable one. I didn't quite prove that to my satisfaction in the general case, but let's just assume this works and run with it. More details in my paper for the masochistic. Okay. So there's a third point, which is that these guys are not null separated. So in order to justify this, I actually am going to skip ahead to my fourth point, and then we'll see what goes wrong if they are null separated, and we'll come back to this, even though logically it should be in the other order. So consider the Maximun surface here. So this is M of R, or I'll call it M. Okay. So intuitively, I want to say that this is an extremal. I want to say this is an extremal surface. So how are we going to prove it's extremal? Well, it's minimal along the surface. There's two normal directions at each point of a codimension 2 surface, and we know it's minimal along one direction, and we know that it's maximal along another direction. So intuitively, it's extremal. But there's a couple things that you could worry about. One is if the surface isn't smooth, then the direction it's minimal in could be different on one side than on the other side. It turns out if you're very careful about the vector spaces, you can still prove extremality. It's just a more complicated construction. But the other thing you might worry about is what if I have since this is required to lie on a Cauchy slice, which can be space-like or null, but it can't be time-like, one thing I could worry about is if there's a null separation between, if there's like a null geodesic separating 2 points on M. So let this be M of R, and let there be 2 points A and B such that they're connected by a null geodesic. That's legal, and when I do this existence proof, I might end up with something like this, but seemingly. But it's problematic because it would mean I'm not allowed to vary my Cauchy slice in all possible directions. I couldn't vary the Cauchy slice to the future this way because now it will be time-like separated to this point. Does that make sense? So in order to make this construction work, I needed to actually prove that this couldn't happen. Fortunately, you can prove that it doesn't happen. How is that? You use these focusing results. So what I do is I start with this light ray here, and I shoot out a set of normal, I shoot out a null surface from the neighborhood of A. And that is going to give me a surface here that satisfies the condition of the kissing lemma. That by causality, it might coincide with M or it might be to the left, but it can't be to the right. And so what we can say now is that, and we can also define the theta of B here. So what we can say is by focusing along this null surface together with kissing where the two null surfaces approach, we can prove that theta A is greater than theta B from focusing and kissing. We can prove that theta A is less than or equal to 0 by Maximun at A. So that's using a variation where I can still vary this guy in this direction. I still know that this guy is minimal when I vary it to the left. Oh, I used the other. It's minimal when I vary this to the left, and it's maximal when I vary this down. So by linear combinations of that, I can get that theta A is less than or equal to 0. And doing the same thing in reverse on the other side, I get that theta B is greater than or equal to 0 by the maximum at B. Note that I'm defining theta to have a consistent orientation to refer to V going this way. So the theta down here has a sort of the theta here are always defined relative to the future instead of, say, inward or outward. So at the end of the day, we get a contradiction. And this stuff can't happen. Okay? So we've now proved it's an extremal surface, but we now have to prove it's in fact an HRT surface. And this one is simple. But this is simple but elegant. So we know that M is minimal on some Cauchy slice sigma. So let us suppose that M is not the minimal area extremal surface, and in fact, that there is another extremal surface that we could worry that maybe it has less area. So what do? We shoot out a null surface from that extremal surface x, and we end up with a sort of representative on this Cauchy slice. We'll call it x tilde. Now, by this sort of by focusing, we know, so by minimality of M, we know that the area of M is less than or equal to the area of x tilde, but that, by number 1 there, is less than the area of x. So we find that x actually has more area. Now you can have a situation where you have two Maximun surfaces that are tied for the same area, but in that case they have to lie on the same Cauchy slice, in which case this could become an equality. Now so this was 5, says it's HRT. 6 is a property that's interesting in its own right, which you already heard about from Xidong, which is now called entanglement wedge nesting. So this is the statement that that if I have a region A on the boundary, and if I grow it to make it bigger, so I replace A with AB, then the statement is that the MAB always lies deeper in the bulk than MA. So it proceeds in a space, it becomes space-like more deeper in. So they can't be time-like separate, and it can't be closer to the boundary. So this is, as you have heard from, so the entanglement wedge is the space-time region that goes all the way between the boundary and this extremal surface. So it's like this entire wedge region that goes to MA that's in here. And so there are now good arguments that she told you about that from this region on the boundary, you can reconstruct the entanglement wedge of the space-time and no more. You can now see that for the consistency of ADS-CFT, this is an important geometrical property to have entanglement wedge nesting, because it wouldn't make sense if I give you more information on the CFT for you to lose the ability to reconstruct something in the bulk, right? If I give you more on the boundary, you need to reconstruct more in the bulk, okay? My Maximun paper was written before this was before there were good reconstruction arguments for this directly. So instead, this is just a sort of consistency property that suggests entanglement. It suggests entanglement wedge nesting suggests but does not imply entanglement wedge reconstruction. Okay, but now it turns out you can also prove this from the Maximun procedure. So you do it like this. You take your regions A and B on the boundary, and we're going to start constructing minimum area surfaces. So this is the minimum. This is the minimum of B on sigma, and this is going to be the minimum of A on sigma. But the key point is that we redo the Maximun procedure with the stipulation that the surfaces A and AB lie on the same Cauchy slice sigma. So I'm just going to put in a constraint that says they have to lie on the same Cauchy slice sigma, and we're going to minimize and maximize a partition function that is given by some linear combination of the area of gamma A and the area of gamma AB, where these guys are positive. Doesn't matter what linear combination you use. Yes?
How do you know you're guaranteed that such a slice exists that will contain both surfaces?
The point is, a priori, we're redoing the Maximun procedure, just imposing that as a constraint. So a priori, it's not obvious that if we impose this constraint, you get the same Maximun surfaces you would get as if you didn't impose the constraint. Instead, we prove that explicitly. So the way you prove it explicitly is first you show that it's not possible for these surfaces to actually cross each other, like this or something. And the reason it's not possible for them to cross each other is that they're both minimum area surfaces on the same Cauchy slice. And so if one of them had less area, so I can take these two things. If one of these two surfaces has more or less area than the other, then I get a contradiction because, for example, I would find that a surface like this might have less area than the surface I said was minimum. On the other hand, if these two guys have exactly the same area, then I would find that there's a tie for a surface like this, and a minimal area surface can't have sharp corners. I could go into more detail here, but I'm running short on time, so I will not. But you can prove it's not like this, where this is like A and this is B. And then that means they must be separated. And that means that I can do these variations of the Cauchy slices in a way that doesn't interfere with each other. And so just by going through all the steps again, I can reprove that they're extremal and that they're HRT. And once I know they're HRT, they're the same surfaces I would have gotten if I had done the Maximun surface variation without this constraint. But now, here's the payoff. Okay, so that makes entanglement wedge nesting clear because they're sort of constrained to go further, deeper along this Cauchy slice. Now we get, as our payoff, we get strong subadditivity. And after all the preliminary work we've done, this part's easy. Although this last step we did of entanglement wedge nesting, that theorem is just as interesting, I think, as strong subadditivity. So it goes like this. We have the key point. So what goes wrong with our proof of strong subadditivity? You remember the original picture proof where we had surfaces like this, and then we had surfaces like this. Okay? So what goes wrong if we're doing it dynamically in space-time? Well, one of the things that goes wrong is that the AB surface may not lie on the same Cauchy slice as the BC surface. It looks like a point here, but because there's time, they may just cross over each other with one to the future of the other. Generically, that's in fact what happens. So we can't put all of these things on the same Cauchy slice. What we can do, however, well, we can put any three of them on the same Cauchy slice, but let's not any three, but three of them, but let's just focus on these two. These ones can be put on the same Cauchy slice by what we just proved, We just do Maximun for them separately and put them together. Then we can't put both AB and BC on the Cauchy slice. We can only put one or the other of them on the Cauchy slice. But what we can do is we can find, just like in this argument, we can find their representative by shooting out a null surface and seeing where it lands. So there's a representative. So these guys are MB and MABC. This guy is the representative M tilde of AB and the representative M tilde of BC. And these guys have less area. So putting it all together, we find that SAB plus SBC, that area is greater than the areas of their representatives, which is in turn greater using the standard picture proof that you would do in the static case of the areas of these guys. So you end up proving that, that the inequality holds. You can do the same thing for monogamy of mutual information. If you like, it's basically the same idea. However, for these more complicated inequalities for 5 or more regions that Ning Bao and his collaborators have discovered, you cannot prove them yet. We cannot prove them yet in the covariant case because the things on the right-hand side of the inequality that things have to be greater than can't be put in a nested form. They intersect each other. Okay. So that's the proof of strong subadditivity and the Maximun results, which hopefully I went through all the steps because hopefully this could be a toolbox to help understand some other GR proofs using the ingredients. Okay, are there any questions about this? Yes.
Is there a reason you can't restrict to space-like Cauchy slices? Does that complicate things?
The step it complicates, that makes the stability thing becomes trivially worse, but now the existence becomes potentially problematic because the Ascoli-Gsella theorem says that you can always find, the topology is compact if the space of functions satisfies some conditions, and one of the conditions is it has to be closed. So the space of space-like Cauchy slices isn't closed because I can take a limit of space-like surfaces that becomes null. So if you're willing to stipulate existence and only worry about the other things, then yes, it works. Yes?
Does all of this rely on like anti-de Sitter space or like negative cosmological constant?
Things go badly if you have a region of space like behind the horizon that has positive cosmological constant, like de Sitter. Asymptotically flat, things also kind of go badly because there's a tendency, you know how there's entanglement shadows, we were discussing entanglement shadows last time in ADS. Well, if you put any positive mass solution in asymptotically flat space-time, then these sort of minimal surfaces go off to infinity. So it's like the entanglement shadow becomes infinitely big once you put any matter in. So that's a little problematic. See, this is why ADS CFT is so much easier than trying to work out flat space holography, because we can think about regions on the boundary and continuously deform them. It's like it's more modular how holography works. Other questions? Way in the back.
And so there's two questions. One is we use this very simplified thing where A and C are three regions, but in general, C probably.
Yes. So this is one particular picture where I've drawn them in a line, but the proof is supposed to work regardless of where I put A, B, and C.
Now, the second question is, you have two inequalities that need to be separated in order to separate structure differentials. You have this kind of triangle inequality, and you also, when you want to have this Cauchy
So you're talking about like the simpler inequalities like Araki, Lieb, and other such things?
I'm asking when you have equality in your proof.
Oh, when do you have equality? Oh, I see. When is it saturated? Usually, you can find situations where this is saturated, but usually it only happens where you take some of these regions where you end up having the like disjoint segments. So, I mean, for example, if I took the 3 segments to be in 3 separate, very far away from each other, so that the AB, the entropy of AB is just the entropy of A plus the entropy of B, then when you have situations like that, you can get saturation. But if there's any non-trivial like intersections of anything, then you can't get saturation.
Do you have examples where the Cauchy surfaces are different, but still the representative remains the same length, the same area?
Oh, so that part, so assuming the generic condition, and the surface is off the Cauchy surface, the Cauchy slice, that inequality is strict. So if you want the representative to have the same area as the extremal surface, then you have to, in that case, you have to have a non-generic spacetime, like maybe ADS or something. But I can't think of a concrete example offhand where this would come into a strong subadditivity inequality. Other questions? Okay. The question is, if I have time to present the gravitational path integral derivation of the Ryutakiyanagi formula, we start 15 minutes because we started 10 minutes late. All right, I'm going to try. Okay, so the one so one preliminary thing, you know, Tom discussed the replica trick for he discussed the replica trick for calculating the entropy. One thing you might ask yourself is he discussed this in the context of quantum field theory. But what if I do it with gravity instead? I could just say I have an action. My actions are always I because S is reserved for entropy. That's the Einstein-Hilbert action, the Euclidean one. Okay, and where I can think of this as being giving me like a partition function. And so what if instead of trying to calculate the entanglement entropy in a quantum field theory that has non-local correlations, I just tried to use the Einstein-Hilbert action? Well, as you know, when I so I could just do this replica trick where beta is the angle of variation. So I'll write this as n. So to match between actions and quantum mechanics, I'll use the log of the partition function is minus I over h bar. So I can use this conical entropy variation formula. When I do this n copies, I get a conical singularity. And as you know, a conical singularity has curvature. And curvature, it's a delta function of curvature, which contributes to the Einstein-Hilbert action. So I don't have time to actually do the calculation, but this, if I say, what would be the entropy associated with the Einstein-Hilbert action? And since there's no actual like degrees of freedom that this is counting, you might think you get something trivial, but you actually get the area over 4gh bar. So this is the sort of Gibbons-Hawking Euclidean path integral derivation of the entropy of, say, a black hole horizon. And this sort of expression is valid when you have something like a stationary black hole. So how do we think about this? Well, it means that somehow the Einstein-Hilbert action knows about whatever quantum gravity microstate degrees of freedom actually go into the black hole entropy. And there's a hypothesis that maybe the black hole consists entirely of entanglement entropy at the Planck scale, which is equivalent to saying that this Einstein-Hilbert action somehow can be, is not part of the fundamental action, but just, this is called the induced gravity scenario. It somehow just comes from the Planckian degrees of freedom. Anyway, what I'm going to show you sort of presumes that you know about this, or are willing to take it on faith. So what Lukowitz, but there are some, for a long time, there are some difficulties in the case where you want to calculate the entropy of a non-stationary black hole horizon, or because there seem to be ambiguities that arose, or difficulties that arose when you don't have this, this rotational symmetry going around. Then the question is, how do you analytically continue this? Oh, I need to put this as n goes to 1. How do you analytically continue n going to 1 when there is no symmetry, so you can't have a space-time? In the context of holography, this was resolved by Lukowitz and Maldacena. And the trick, which I may end up skipping some steps because of the time, but I can at least outline the basic steps here. The trick, so we have some path integral to derive our state, and the path integral might have insertions, or it might have background geometry of some sort that makes this not stationary, or I might just pick some funny shaped region on the boundary where I don't have any symmetry. So I have this region here I want to calculate the entropy of. So what I do, so since this is ADS CFT, I have that Z boundary equals Z bulk, which implies that the effective action of the CFT is equal to the effective action of GR in the bulk, where these can both be written as minus log of the partition function. Okay, so we're going to use the classical geometry and action in the bulk to get the quantum one on the boundary. So the key point is when we do this replica trick, we calculate the bulk instanton solution that is associated with this thing. And we could call that M of n. And there's a conical singularity on the boundary. So you might have thought that there would be a conical singularity in the bulk too. But there isn't. There can't be, because by definition, the bulk thing is supposed to be a solution to Einstein's equation, and the conical singularity in the bulk would violate Einstein's equation. So even though the boundary is not smooth, if you go even a little bit into the bulk, it needs to become smooth. Okay? So that's the key point, one key point, that Mn is smooth. But what we do instead is that we notice that there's a Zn boundary, there's a Zn replica symmetry, not that kind of Z, this kind of Z. There's a Zn symmetry on the boundary. The assumption we make is that this symmetry is not spontaneously broken, so that there's still a Zn replica symmetry. There's still a Zn replica symmetry in the bulk. Okay? This allows us to pick out a special surface that lies inside of this smooth geometry. The special surface is the fixed points of the Zn replica symmetry. Okay? So this is just a surface that lies in the smooth thing around which the, at this surface, if z is 3, so since this is smooth, there's just 2 pi worth of angle, but if z were 3, then there'd be a z3 replica symmetry going around this where everything is copied 3 times. Okay? Makes sense? Then what we do, and here's the clever thing, is we orbifold this space-time. So we consider a new space-time geometry that's an orbifold geometry that is Mn modulo this Zn group. Okay? Now, this is the important thing to emphasize is this is just a trick. Okay? It's just a sort of mathematical trick. I mean, maybe there's deep physical significance, but we don't justify this by saying that that the bulk is actually different. So instead, we just have to define what we mean by the action. And by convention, we're going to define this action to be I of On is equal to the action of M divided by N. So we're just saying it's the thing where if I copy it, say, 3 times, I get the original action. We do not include a boundary action coming from the conical singularity that results after we orbifold. So after we orbifold, it's like there's a brane there whose gravity produces a conical singularity, but the brane doesn't really have an action that contributes to the action of Mn, because of course the real space-time is the smooth one, the actual space-time associated with the N replica. So what we do, so one way to think about this is that we have On is a solution to an action that consists of GR plus an action that consists of the brane, but this term is not included when we actually evaluate the partition function at Zn. So we could say that there's this brane action that's effectively there to produce this conical singularity, but it isn't really contributing to the action. Is this clear so far? Yes.
Why should the Zn fixed points be like that in the bottom?
So it's just it's sort of by, if you look at the boundary, other than the boundary of this region, the Zn maps points to other points. But at the entanglement surface, it's mapped to itself. So just sort of by continuity or some sort of topological thing, as you go into the bulk, there must exist some set of points that map to itself. And it's like a brane that has positive action. It's like a brane that has tension. And because it has tension, it's going to extremize where it lies. And you can, in fact, analyze. So you can just start with the gravitational action of this thing and analyze that after you do the orbifold, it behaves just as if it had an action that it was minimizing. But the brane back reacts on the geometry because it has positive tension. And that makes this different from the original thing. Now, once we do this orbifold, oh yes, one extremely important point is that the boundary of the orbifolded manifold, because we've modded out by this replica symmetry, the boundary is the same as the boundary of the original manifold. Okay? So the amazing thing about this is because the boundary is the same, and the brane action this guy is proportional to something related to 1 minus n. So this thing is proportional to n minus 1 somehow, at least for n approaching 1. I'm not going to examine my algebra enough to know whether that would be 1 over 1 minus n or something. So the point is, this whole setup now, because the boundary is now fixed, it now makes sense to analytically continue to non-integer values of n. Okay, so you can do the math to see what that analytic continuation looks like, but here's the key physical point. We're interested in the limit as n goes to 1, right? So n equals 1 is a solution to the equations of motion. Now, as you know, because then there's nothing special. As you know, if you do a first order perturbation to a solution, that has the property that the variation of the action, or the effective action if we're doing quantum mechanics, is 0. So for purposes of this limit, as we take first order variations as n goes to 1, we find that we find that in this limit, the sum of the variation of these two actions is equal to 0. Now here's the other clever trick. We can therefore replace, so before I said the brain contributes no action when we're calculating the final partition function. It only comes in as a sort of effective way to find this orderfold solution. The true action comes only from IGR, but that's a bulk integral over all d dimensions. But because of this equation, we can now say that delta IGR equals minus delta I brain. So at the end of the day, you find, and the action of this is proportional to the area. Furthermore, since in the limit that n goes to 1, it's like a test brain whose tension is very small, the location of the brain is just, it's like a test brain, so the location of the brain in the limit that n goes to 1 is just the extremal surface, because that's what minimizes the action of the variation. So since I don't have time to do the algebra, I'm not going to do the algebra, but you can either work through the algebra yourself or look at their paper, and you find, doing all of these steps, that you end up with the value of this formula is going to be equal to the area of the extremal surface. And that's this proves Ryutaki-Yanagi, because they were assuming that the geometry is static for purposes of assuming that the Euclidean spacetime is just a Euclidean spacetime with no complex metrics or anything. Okay, so they proved Ryutaki-Yanagi for the minimal area surface. But then there's a number of extensions. Faulkner, Lukowitz, and Maldacena repeated the same steps when there's a quantum field on the space-time, and they ended up with a bulk entanglement entropy term. Shi Dong looked at higher curvature gravity, and he found what entropy function we get for higher curvature gravity theories like Lovelock or other things. He found that allowed us to work out terms like extrinsic curvature squared that appear in the black hole entropy that we couldn't work out from like the Wald Eier type methods than other charges. And finally, Shidong, Mukund, Rangamani, and somebody else looked at, Aitor, I think, looked at, Aitor Lukowitz, they showed that this argument does work in the dynamical case where you're proving HRT. So what I just showed you, although it's the sort of simplest form, it has been fruitfully applied to all of these extensions to generalized entropy for higher curvature or quantum situations. Okay.